All right, here's some feedback or things to talk about for your poster. So I'm not going to write your poster presentation for you, but just go through the figures. So in this figure, what's important to talk about is the orange channel 1, which is the noise, and that in the experiment, you're varying the peak to peak of this noise, which translates to the RMS, which you square this and integrate it, and it's kind of like an average, right? And then this is your sine wave, right? Which you have to clearly state what the peak to peak and the frequency was of yours. But notice how that the peak to peak of the noise is greater than the peak to peak of the signal we're trying to detect. Use this symbol over here instead of the one you found, where we have the input on the negative terminal and we the noise, and we have our sine wave coming in on the positive side. And that this is a Schmidt trigger with hysteresis, right? And now that's probably when you should do an intuitive explanation of what hysteresis is in your own words with like your own example, right? That anybody can understand. All right, I've been asking this for a while. I haven't really heard it yet, but we got to get her done. Okay, then in the next part, it's more of your experimental, and here's the frequency spectrum of the noise, right? You can see that up till about, we're having like a roll off of at a couple, like 300 hertz, right? But that this doesn't, that if the amplitude were to be bigger, this whole curve would shift off, but that if it was smaller, if that peak to peak of the noise was smaller, this would all go down, okay? But the drop off would be the same. All right, then you explain your circuit that this is a current source that sends a current through a voltage, V equals IR, and then you put it into a buffer so that then you can input it into your Schmidt trigger. This current source is controlled here, and it either gives just a DC value or a DC plus a sine wave, right, which you set in programming. Now here you probably want to take a picture of what you did your hysteresis with and label the hysteresis with points. Right, this was from another paper. So what was your measured hysteresis with? There's two of them, right? How to compare it to your theory? Go back to the tutorial and look at the notes. I showed you how to do that. All right? Now, yeah, the experiment really is we did two things, right, at medium power, medium compensation, right, and then you did your own and compared it to high compensation, low power, and high power and low compensation. Okay. This is what the results should look like. These are your actual figures. Oops. Okay. And then I actually did these, and you're free to use it. But this is your data. All right. And so here is the transient, and we're measuring full width half maximum, so there's no sine wave here. Right? We collect the data and we do a frequency power spectrum, which is similar to an FFT, and we're finding the frequency components. And we curve fit a Lorentzian to this, and it calculates the full width half maximum. So this full width half maximum here and that theta there goes over on this plot, although it's 1 over theta. So that's really close to 1. No, excuse me. That's more close to 10, right? So it's this point. It's near this point. For this was for mine, for medium power, medium compensation for my circuit. But I'm saying is one of these generates a point here. Changing theta keeps generating the points. All right, and this one is supposed to have medium power, medium compensation, and high power. Oh, that figure's not right. Because Eric should be low power, high compensation. I just cut and paste it. So we'll have to fix that. But I'm missing one of those data sets. Right now I did a curve fit here, and the curve to the constant is e to the 11th, and the delta u is 0.393 divided by theta. Then this is your signal to noise ratio, but you got to put in what was your VP, what was your V reference of the sine wave. Oops. I'll fix that later. Okay. Over here, or so I should say, one of these makes one of these plots or one of these plots. Now here we've added a sine wave for the same input noise, and we're getting a signal to noise ratio at 1025 hertz, which is this here, which I would actually draw on that, right, in some kind of PowerPoint thing to highlight that. This is without it, and this is with the sine wave, and that, notice it kind of makes the noise go down everywhere else. All right, so one of these plots makes a point over here, right, and that there wasn't any appreciable difference between medium power, medium compensation, and medium high power, low power, high compensation. I have that wrong here. I'll have to rerun it, right? And here in the peak range, it does look like the high power, low compensation is more sensitive, because if you look at the error bars, it's well above. But that the flat zone is still in the same place. Then on the plot where you say other interesting points, just say you did 4 PSOC projects and put in things about the breathing, proximity detector, temperature measurement, and the digital logic part. Just try to summarize those 4 things that you did. Here I've just, I got to just re-edit that in Python and rerun those plots. But again, we need the comparison here. Otherwise, we don't know what we're doing. Okay? So that should be enough to get started with.